What's up, AP Calculus students? Mr. Ford here with the Chapter 4 review. I'm probably going to end up doing this in two parts, so I think this video will probably be just 1 through 10, maybe more. We'll see how far we get. So, first we got to write a Riemann sum using three left endpoint rectangles under the curve, that thing, from x equals 3 to x equals 4 using sigma notation. And how could you modify this to get an exact answer? Now, I'm going to answer the second question first. How could you modify this to get an exact answer? And just write the integral. I think that's probably the most important key. So I'm going to put number 1 over here. I mean, what I need you to understand at this moment is that we're just going to write this as the integral. Let me get calculator cam out of the way because we will not need it for this problem. This is the integral from 3 to 4 of that function, 2 to the x plus x squared plus 1 dx. That's the answer. But it's important to understand the bones of what's going on here. So this is going to be equal to the following limit expression. Limit as n approaches infinity of the sigma from I equals 1 to n, meaning that we're going to go from 1 to infinity. And from here, we're going to need a couple parts. The first thing we need is the width of each one of those rectangles, which is going to be the delta x piece, which we typically do by taking a minus b, in this case 4 minus 3, and dividing by n. So I'm just going to write 1 over n here as the width of each one of those rectangles. The next piece we have is f of the left endpoint, 3, plus 1 over n times I, like that.
Hey guys, I need you to... The mic's on, so shut up.
That's all well and good. The tricky part here is plugging this expression in for x in the original expression, which is going to make it look a little bonkers, but it's not too terrible. It's just important that you understand what's going on behind the scenes here. I equals 1 to n. And we'll keep 1 over n right there. And as far as f of this function goes, well, it would be 2 to the 3 plus 1 over n I power. There's your 2 to the x power. Plus 3 plus 1 over n I squared plus 1. And that's your the height of each rectangle that we're going to draw. So, I mean, I think that's bonkers, and you would never do it that way. The integral is much more expressive, but that's where the integral comes from. In the end of the day, it's nothing more than length times width on this rectangle. Let's look at question number 2. We're going to find the slope functions, or f prime of x, for the following functions. It's important that no matter how far we get into this class, that you never forget that f prime is just the slope of a certain function. I think we have enough space to do these right here because it's relatively simple. The only thing I would remember is that f of x, in this case, I would rewrite this as 6 times x to the 3/4 power. You can rewrite that root expression like that. It doesn't really matter what the square root of pi to the 5th is because that's just a constant. So when we take the derivative, it will become 0. And then b looks pretty good also. So when it comes to writing f prime of x, all we got to do is use the power rule. 3/4 times 6 will give us 18 over 4, which I know reduces, but I'm going to write it down for now, times x to the negative 1/4 power. And then the square root of pi to the 5th is just a constant, so it becomes 0. We can simplify this a little bit. Let's see, 18 and 4 both divide by 2, so it's 9 on top and 2 on bottom. And let's just put the 4th root of x down in the bottom there, because that's the x to the 4th power down below. That would be the simplest way to write that answer, I think. For question B, we can just take the derivative of this right now because it's already in polynomial form. You're going to have 5/2 x to the 4th, 4/3 x to the 3rd, and then minus 3/4, just the constant fraction, the constant coefficient there in front. Not too tough. There it is. Question 3, does the integral from a to b of f of x equal the integral of a minus c to b minus c of f of x minus c? The answer to this is no, and I'm going to explain clearly and show you how to fix this so that it does work. It's really close. This would be the case if this was x plus c inside. And this is all about translations. Which way are you translating? Let's draw a picture really quick to help explain what's going on here. This is for number 3, off to the side. Just sketch yourself a basic, here's a, here's b, and here is the original curve like this. Doesn't really matter what it is. All you know is you've got the area between a to b underneath some curve that we're trying to find the area of right here. That would be that yellow space there could be expressed as the integral from a to b of some function f of x dx. Now, what's happening here is that if I suddenly say, hey, I want to do the integral from a minus c to b minus c, what we're going to do here is we're going to take those endpoints, or those boundary points, and we're going to slide them backwards some number of steps. Let's call it c. And it's got to be the same in both cases. So what's happening is your goalposts of your integral have now slid to the left, c number of spaces. That now is a minus c. And that point there is b minus c, and that's the new integral. The problem with f of x minus c is that if you remember how translations work, this moves to the right c spaces. So this is now taking the function and moving the function to the right c spaces, which would make it look, I don't know, I'm not going to try to draw it, but you got to imagine you're going to move the goalpost this way and the function that way. You're going to end up with an entirely different amount underneath the curve from a minus c to b minus c. Now, if you want to fix this, what you're looking for is the integral from a plus c to b plus c of f of, or sorry. No, that would work. Of f of x minus c dx. This would work, because now you're moving your boundaries to the right and the function to the right. Alternatively, you could also do the integral from a minus c to b minus c of f of x plus c. This would move the boundaries to the left and also the function to the left. So these two are true. But this one here is not. That's the difference. Let's look at 4 for a minute. We're going to evaluate a bunch of integrals here. I'm going to do as much of these by hand as possible, just to remind you how that's done. Well, actually 5 and 6 you would have to do by hand. So number 4, you could make the case that's a calculator question, but it's actually not too tough to do. So we're going to do number 4. I'm going to write it down off to the space here. This is number 4. This is the integral from -1 to 1 of 3z squared minus z plus 1 dz, like this. So what we're going to do here is we're going to find the antiderivative of that expression, which is actually pretty simple to do. That's z to the 3rd power minus z squared over 2 plus z. And we're going to evaluate this from 1 to -1. Meaning we're going to plug in 1, plug in -1, and then subtract. And that's a pretty simple thing to do. If you plug in 1, you end up getting 1 minus 1/2 plus 1. And then if you plug in -1, you're going to get -1. Let's see, this would be another minus 1/2 minus 1. So if we shake all of this out, I mean, I'm tempted to just cancel out the -1/2 there, because they will cancel out. Actually, I do kind of want to do that. Here's the way to think about this. This is -1/2 right here, and that's minus -1/2. Those are going to cancel out. And what you'd be left with is 2 minus -2, which I think equals 4. And that's the answer I'm going to go for. We'll give that a quick check on Calculator Cam just to confirm that it's right really quick. Let's see, the integral from -1 to 1 of 3x squared minus x plus 1 dx. And it should be 4. Yeah, it is. So we're good to go on that one. You should be prepared to do an integral like this by hand. I'm just saying that calculators are great, but you might get a question like this on the AP Calc test. That would be a reasonable thing for you to do without a calculator. For question 5 and question 6, we're going to be able to do these without the calculator because they are not definite integrals. Number 5 is, sorry, I'm a ding-dong. Number 6 is not. 6 is an indefinite integral. But 5 is also super easy to do. I mean, even if you were to use the antiderivative, this would just be the square root of 2 times x. Actually, it'd be better if we wrote it as x square root of 2, just to avoid confusion. And we would evaluate this from 11 to 6. And what you'll find when you do that is you're going to get 11 roots of 2 minus 6 roots of 2. And if you factor out the square root of 2, this is just 11 minus 6 times the square root of 2, or 5 roots of 2. The reason why that's simple to do without even doing any integration is that, don't forget, we're looking for the area under a curve, and this is a constant function. So what you're going to be doing, if you were to draw a graph of this, let's say this is 6 and this is 11 right there. Let's make that a bigger 6. This is just going to be a horizontal line like that. And so the area you're looking for ends up just being a rectangle. And it's a rectangle with 11 minus 6 or 5 on the bottom and square root of 2 on the side. So it ends up being 5 roots of 2 no matter what you do here. Not too tough to do. Now for number 6, we are going to need to do a little bit of prep work before this because we don't have a tool for integrating this on its own. However, I suspect that the top of this fraction, if we factor it, will contain the factor x minus 5, and I'm pretty sure it does. In fact, I'm so confident I'm even going to write it down before I start. So what I need now is I need something that multiplies with 5 to make negative 5 to make 20, so plus 4, and that does give you the negative x if you multiply it all the way out, dx, and so these guys end up canceling right out, and so we get the integral of x plus 4 dx. And this is an indefinite integral, so our answer is just going to be an expression with a plus c attached. It'll be x squared over 2 plus 4x plus c. And that's all you need to do there. Don't forget the plus c, though. Question 7 is going to ask, what's the difference in area between 5, the integral from 5 to 11 of some function, and the integral from 5 to 11 of some function plus 10? Let's draw a picture to explain what's going to go on there. I'll tell you the answer right now. The answer is going to be whatever 6 times 10 is. 60. That's the answer. But with that answer written down, let me draw a picture to explain how I know that's going to be the case. Let's just picture for a minute. This is question 7. I'm just going to try to keep my drawings together today. Let's just picture for a moment what we're talking about here. We're talking about the integral from 6 to 11. I'm just going to draw a quick sketch of some function we'll never know. And we don't know what that area is anyway. We'll never know what this area is. But if we add 10 to it, what happens is we move the function up 10 spaces. We just take a vertical translation, and the new function will be exactly the same as the old function, just moved up 10 spaces. So you're still looking for that same area. But now the difference is there's going to be a new, you're still going to have the existing area you had in the previous problem, but the difference is that now you're going to have a little 10 by, is it 5? I might have made a mistake on my original answer. I apologize for that. You're just going to add a little 10 by 5 rectangle to the bottom of it because you're moving the problem up 10 spaces. So you're just going to add a rectangle on there. So, yeah, I withdrew. Oh, no, it was 5 to 11. I was right. I just drew the picture wrong. Ha. Cool. So you're adding a little 60 units squared onto the bottom of an already existing area, and that's why it's 60 units squared. I think about that. As far as fundamental theorem of calculus part 1 and part 2 goes, depending on which textbook you ask, if you were to Google this question right now, you could find a pretty good answer. Depending on who you ask, part 1 and part 2 are two different things, but there are two that you must need and that you must know. The first thing you must know is that if you were to take the derivative with respect to x, ddx, of an integral from some constant a to x, of a function f of t dt, if you take the derivative of an integral, they cancel out. And what happens here specifically is that this x inserts itself into the function, and now you've got f of x right there. That's it. That's part number 1. Derivatives and integrals are opposites of each other. The part 2 is going to be that if you have an integral from some a to b of f of x dx, the way that you evaluate this is you find what's called the antiderivative, capital F, of b, and you subtract capital F of a, which we've used a couple times here. So I guess the way I think about this, there are two parts to it. One of the parts is that they are opposites, so I just think about the word opposites. And the other part is how to evaluate definite integrals. Both parts of the fundamental theorem of calculus, though, just deal with the idea that derivatives and integrals are opposites of each other. If you take the derivative of an integral, it cancels out, and the x plugs itself into the function. And then you can evaluate an integral by finding the antiderivative and plugging in your b and your a and subtracting. These two ideas vibe together pretty well. Those are the fundamental theorem of calculus, parts 1 and part 2. Number 10, a shoe falls off the rock climber at 500 feet. The velocity of the shoe is given to us by this velocity function. What is the velocity after 1 second? Okay, that's an easy question to answer. I'm going to do it off to the side, though. I need some room for this question. I'm going to do it over here. This is number 10. I'm going to draw a little box around my work here. They did tell us that v of t is equal to negative 8t minus 10. When they want to know what the velocity is after 1 second, really all we got to know is what's v of 1. It's really simple. In that case, it's just negative 8 minus 10 or negative 18. And our units here in this case are feet per second. That part is relatively simple. The next question will be a little more tricky to answer. Where is the barrel after 10 seconds? Where's the barrel? What barrel? I think somebody wrote this story problem and got their wires crossed. I thought it was a shoe. Let's assume we're talking about the same thing. Whatever, shoe, barrel, let's assume they're talking about the same kind of problem. As far as where it is after 10 seconds, that's a trickier question to answer. We know that it originally started at 500 feet. I would call this S sub 0. In other words, the initial position. And we know what its velocity is, but what we want to do is we want to add up those velocities over time to find out a change in position. So this second question there is going to be a lot trickier to answer. I'll set it up for you and then remind you how it's going to be done. What you're looking for, you know that the barrel was at 500 feet, but then you know that it's going to drop and it's going to start gaining velocity as it drops. So to that, we're going to add up, we're going to sum up all the velocities from 0 seconds to 10 seconds of our velocity function, v of t dt. I'm going to draw a line here so I don't get confused. What that means for us is we're going to need to evaluate this integral. Negative 8t minus 10 dt. That's not a particularly difficult thing to do. I'm just going to take the antiderivative right now. It's going to be 500 plus negative, let's see, I got to think about this. It'd be t squared. That would be negative 4. Put this in its own little brackets there. And then minus 10t. And we want to evaluate this from 10 to 0, essentially. So not forgetting about the original 500, because that's part of this problem. We're then going to need to carefully evaluate this integral. The nice thing is that we're going to plug in 0 for the second part, and plugging in 0 to this function will just give you 0. So we don't really need to worry about that second part so much. This is going to be negative 4 10 squared minus 10 times 10. And again, there is a minus 0 on there, I guess, if you wanted to be technical. So we got our original 500 plus the change in position, which we found by taking the integral of velocity, essentially. That's going to be negative 400 minus 100. I think if I'm doing that math right, which is negative 500. So this is going to be 0. So I suppose the answer to the question is, where is the barrel or the shoe after 10 seconds? It's on the ground. That might be a good question. 0. The next question is even easier to answer. Where is the barrel after t seconds? Again, let's assume we're talking about the same thing. This is going to take our work from the previous problem and just make it more general. We're just going to kind of build a formula out of it. I'm going to go over here. It's just going to be the original position. Let me write it in formulas first, and then we'll make it good for our problem. We want our initial position plus the change in position, which we can find by doing the integral from 0 to t, or 0 to x, I suppose, of v of t dt. So if we plug in the information that we know about this problem, we know the initial position of the shoe was 500 feet above sea level, plus the integral from 0 to x of this velocity function, negative 8t minus 10 dx. And so if we actually were to evaluate this, we could take the work we did and take the antiderivative. Let's go even further. It would be 500 plus negative 4x squared minus 10x. And you could even, from here, make it a parabola if you wanted to. It'd be negative 4x squared minus 10x plus 500. There you go. That's the more general version of what we did in the previous problem. Let's see, looking at my time, we got one more to do here, and this is a really simple one, so let's look at 11 really quick, and then I'll close this video out and work on another one later on. Actually, we can do 11 and 12 side by each, because they're, we can do 13 also. These are really simple. And I'll save 13. Let's just do 11 and 12. 11 is going to harken right back to the fundamental theorem of calculus that we talked about a minute ago. The derivative, we're doing the derivative of an integral, and those things are opposites of each other. The cool thing is that this doesn't actually do anything. The number 5 doesn't matter at all. It's just a constant. We're talking about how this thing is changing. So what we're really going to do is plug x into the function, which it's already there. So the answer here is just going to be 3x plus 1 to the third power. That's it. There's nothing more to say about it. The derivative and the integral cancel each other out. That's it. Now, 12 is very much the same thing. We have the integral of a derivative this time. The only thing you got to remember here is the order kind of matters when you're doing this. The integral and the derivative are going to cancel each other out, but what you're going to be left with is the antiderivative of this thing. And that's asking what's the antiderivative of that derivative. And so the answer is going to be this kind of the same, 2x minus x squared, because that's the antiderivative of the derivative of 2x minus x squared. But you also have to remember to put a plus c on there because the second step, or the last step, was to do the integral. So you do have to put a plus c. The idea is if you took the derivative of this thing, you would get the derivative of 2x minus x squared. And the c wouldn't matter because it's going to become a 0 when you take its derivative anyway. Pretty straightforward. I suppose we could try this last one really quick. It's not going to be too terrible. Actually, it's really simple the more I think about it. Let's just look at what's going on here. You're going to take the derivative of the integral from 0 to 1 of cosine 3x plus 1 times square root of x. I mean, you can use a calculator if you want to evaluate what this thing is worth, but it's going to be worth just a number. So you're going to be doing the derivative d dx of some number, and it won't matter because it will be 0 no matter what. If you take the derivative of a constant number, it's always going to be 0. So since the definite integral gives you a number answer, just take the derivative and it'll be 0, like that. I'll stop this recording now, and I will work on the other problems later on today. Thanks for being here. You guys are awesome. I'll see you in the next video.